I'm a master's student at Bishop's University, and so I'll just jump right into learning around galactic foregrounds. So sort of the object which we are interested in is this H1 21 centimeter signal from like reionization era redshifts. So redshifts around 10 up through 20, that sort of era. And we're trying to probe that era for the highly redshifted 21 centimeter signal. As we saw in the last talk, one of the huge obstacles to get in the you have to get over in order to actually make a measurement of that signal are these galactic foregrounds. And I really like this figure here because it shows this little medieval observer. And in the Middle Ages, the firmament is this barrier between the material and heavenly worlds. And so in our age, we do have our own firmament in the form of this galactic overwhelming foreground. It's 10 to the 5 times brighter, greater in magnitude at our target frequencies than our target signal. And so it creates this kind of a insurmountable barrier, which just obfuscates the entire signal. Lucky for us, this foreground is predictable. This is a really great figure from a Pober paper, 2014, which shows us in cylindrical Fourier space, sort of the blueprint or the footprint of the galactic emission. And so in this figure on the right, I show that the galactic emission is sort of contained here in this wedge and intrinsic foregrounds region along the perpendicular K modes in the sky plane. Whereas in this region, which is called the EOR window, those Fourier modes should be mostly free of contamination from galactic and extragalactic sources. So the end goal of this research project is to take advantage of the wedge in order to perform foreground recovery rather than foreground subtraction. So what's the nuance here? What's the difference? In a foreground subtraction model, you have essentially 2 humongous numbers. One number is the signal plus the huge noise, and then the other number is your perfectly calculated noise, which you will then subtract out and then produce your signal beneath it, which is, once again, much smaller and very specific. You have to get the model of the galaxy just right for that to work. So we're not doing that. We're doing so-called recovery, where we're just going to throw away any data that we think has noise in it, just throw it out. And then based on what's left, we're going to reconstruct what we threw out. And so why is that reasonable? Why is that possible? We'll get into that. So, as many are aware, we don't have good tomography image data from the reionization period. So we use simulations from 21cm fast. It's from the Messenger et al. Group. And so this is sort of the kind of basic, it's a semi-analytic, it's fairly cheap to run. And so you need lots of data in order to do machine learning, and doing those gigantic hydrological simulations would not be efficient or a good use of time. And so just to really illustrate the effect of the wedge of the Milky Way foregrounds is, so if I take the Fourier transform of this simulated map and then just zero out all of the wedge modes, all the modes that exist in this wedge region, I just send them all to 0, and then inverse Fourier transform back to real space, I end up with this picture here on the right. Nothing of interest or value remains. You're just throwing out so much data that whatever's left is there's nothing visibly interesting there. So let's get into the kind of the reasoning behind why you can do foreground recovery as it is. And the reason is that the 21 centimeter signal is expected to be non-Gaussian. And so on the left, this is just a very simple diagram of, let's say, a Gaussian distribution of vectors, where the vectors have random magnitudes and random phases. In a non-Gaussian distribution, you have potentially random magnitudes, but there's some correlation between their phases. So here there's a very clear pattern with the magnitudes and the phases. On the left, there is no pattern. If I were to remove one vector from each distribution, and tell you to guess, okay, now add in the missing vector. You can do it for the right because it's non-Gaussian and you see the pattern. On the left, you could do no such thing if you didn't know what the original image was. So this is a really simple version of the philosophy behind this project. Hey, well, if it's a non-Gaussian signal, I can throw away an arbitrary number of vectors, and as long as I have a few left over, I can kind of figure out that covariance matrix and reconstruct all of the missing vectors that I threw away. So how do you solve it? This is sort of the Hail Mary of physics is the neural network. You just throw it at machine learning. If you don't have an explicit mathematical solution, or it's a nonlinear regression problem. There are reasons to do machine learning, but that's what we go for. So this is sort of the very simple. This is the idea. We're going to throw in wedge affected images like this one on the left. And the idea is to allow the network to get to a point where we can just see that and then map right back to a non-wedge affected version. And so just to kind of connect with the last talk, okay, this is sort of the an underlying message here is that this is a image space sort of problem. He talked about Fourier space problems you can do and image space problems, and there are, say, 2-point, 3-point statistics. There's mapping. This falls under the image space sort of problem solving type of project. So one thing neural networks are great at is image segmentation, where I throw a picture at it and it says, okay, well, all these pixels here, that's a bicycle, or that's this or that. And so we just turn this into a classification task where we say, okay, take every pixel and tell me if it's ionized or neutral. And here ionized means fully ionized, and anything less than that is just considered neutral for the sake of this classification. Okay. So we have data set from various neutral fractions spanning redshift 7.85 through 8.5. And I'll just show you right ahead the results, and they're very promising. So if you look on the far right here, that is a wedge affected image, which is passed into the network. It's associated, if it were not affected by the wedge, with the image on the far left. If I were to binarize that image, that's this binary mask in the middle left, and then the middle right is actually what the network predicts. And this is not an image that it was trained on. This is sort of what's called like a validation image. So it's able to produce that from the image on the right. So we up the ante a bit, simulate some instrumental noise for Hera and SKA, and we find that even for Hera and SKA, I mean, this is on the image on the right, this far right here, that's the wedge plus Hera instrumental noise affecting that, and it is still able to reconstruct some kind of bubble distribution, and similarly good, if not better, results for the SKA. So we run it through a null test, make sure, okay, is it really exploiting non-Gaussianity here? In order to test that, we Gaussianize a map where we transform it to Fourier space and then randomize the phases of each Fourier vector. If the Fourier vectors have a random phase, then there's no longer going to be that covariance matrix, and it should fail. And indeed, the network does fail to reconstruct anything when we Gaussianize the map. So yeah, just works. It seems to be working pretty well, and this is kind of an avenue of continued work and exactly quantifying what are the limits of this at what redshifts, and what else can be done with this kind of a project. And so I think I'll just open it up to questions right now.
Thank you, Sam.